Good evening, everyone. Today, uh, we are going to discuss about week 8, and we are going to solve some problems which are going to hopefully help you solve the assignment of week 8. So, this is week 8 problem solving session. So, as you all know, this same course is taken by Professor K. Ramesh from IIT Madras, and my name is Syed Shabir Ahmad. I am a PMRF scholar in the Department of Applied Mechanics and Biomedical Engineering from IIT Madras. And my areas of research or interest lie in the field of digital twins, structural monitoring data, and the pilot dynamic model of data and its allied areas. So, first, we will start a session. Some so this week it was uh, totally uh, dedicated to bending or flexure and how we arrive at evaluating the bending stresses from bending strain and how we get a flexure formula and some uh, engineering analysis about beams. Different things were discussed in this week, and primarily it was completely bending. So, whenever we say bending, we are here talking about pure bending. Pure bending is when only bending moment is present and shear force other things are zero. So we can see how we can go to shear stresses, how you can uh, include them in your design and analysis in the next week. So because we are uh, mainly dealing with linear uh, problems, so whatever we take, we can usually get a bending stresses, shear stresses, and axial stresses, and we can sum them using principle of superposition because as long as the problem is linear, we can use the principle of superposition to get the whole effect of it, each and everything. So the first thing we have seen is we can we have seen that bending stresses uh, very linearly like this. Suppose if I have a beam subjected to
Hi, sir. Good evening.
hi Devasis, how are you?
Fine, sir.
Okay.
Sorry, sir, little delay.
Yeah, it's fine. It's fine. So are you settled?
Yes, sir. No, okay.
Okay. So this week we mainly dealt with bending or flexure. So whatever it was discussed in the three videos of three lectures in the week was completely related to bending. And bending, in the sense here we are only talking about pure bending. So pure bending means there is only bending moment and bending moment present on the beam, and shear force or axial force or twist torsion, other things are not present here. Only bending moment is present. So other things we can include it as long as our problem is linear. Whenever we say as long as the deformations are very small, then we can take it the problem as linear, and you take shear stresses separately, bending stresses separately, and you have any axial force due to that axial stresses separately, and you can combine the whole thing using principle of superposition. So here we are only concerned with pure bending. So pure bending uh, like uh, we have seen like how we get the bending strain, and using the deformation, and how we get uh, the bending stresses, and how we get the torsion formula, which whatever it was discussed. And we have seen that whenever a beam bends like this, there is a axis which doesn't deform, uh, which is called as a neutral axis. So if we have a beam like this, here whatever we are discussing is at this plane of symmetric surface which passes through the section like this. So only we are talking about this surface, symmetric surface. As we go away from this, there is effect of Poisson's ratio and all. This is the thing we are talking about here. Uh, and other thing is in this we are only talking about sections which have a vertical plane of symmetry like this. Or if load is applying, if load is being applied, that should be applied on this vertical plane of symmetry, like different sections. This has a vertical plane of symmetry. This has it. So if you have a section something like this, cross section something like this, we are not dealing with this here because uh, whenever a load is applied on this, there is also twisting which happens. Uh, that we will see in further lectures, which is called unsymmetric bending. So we are not dealing with this here. So only this kind of sections which have plane of symmetry. So whenever a beam is deformed, we see that there is a axis which doesn't deform, which means that the length of this axis, neutral axis, is same before and after deformation. That's why it is called as a neutral axis. And in this, you can, this is the neutral axis, let's say, and the neutral axis uh, here is also coinciding with the centroidal axis. Huh. So we have seen that bending stresses vary linearly from at the center bending stresses are 0, and at the extreme fibers bending stresses are uh, uh, maximum. So if I have a beam like this subjected to pure bending, which is a positive bending moment here, uh, and it is subjected to like this, the top fiber will have compression, and it varies linearly from the center, and it reaches maximum at the outer fiber, and the bottom fibers below the neutral axis uh, have tension. So bottom fibers expand and the top fibers above the neutral axis uh, basically uh, get compressed, and or you can say the length is shortened, whatever. So you can see that the central part of the beam is not taking its central section. If you have a section like this, let's say this is a rectangular section, this section is not taking most of the bending stresses. So in engineering design, lot of times you can see I sections uh, coming up like this for beams, because material can be saved and these are more efficient, and the moment of inertia increases for I section, because as you can see the material goes away for same area of cross section. If you say rectangular cross section and I section, rectangular section and I section, which is efficient is for same, if they have both same area cross section, I section will be having higher moment of inertia. That's why it will be more efficient. Uh, can you hear me, Devashish?
Yes, sir.
Okay. So the Euler-Bernoulli beam theory, whatever we have discussed in this week, Euler-Bernoulli beam theory is applicable for uh, only symmetric cross sections, cross sections which have some symmetry about vertical axis, or which uh, on which the load is applied, and also like thickness or breadth should be comparably low. Breadth, sorry, depth of the beam should be low. So that depends if the depth is less, or if the depth is more, little bit higher, or comparably along with length, the depth by length ratio of the beam is high. There is some ratio. I don't remember the exact number, but if it is high, uh, what happens is that uh, this uh, plane section is not perpendicular to the neutral axis, and it makes some angle with it. due to the shear. So we cannot neglect shear in tim uh, beams which have greater depth. So that's why we go for other beam theories. And also we have seen transmissibility of force, how force is uh, taken from one point to the other. Let's say if we have a force uh, F at point A, and if I want to shift this force to point B, so I should have something extra, which is let's say I can like a force direction. So there is no effect on the B point. Net force is zero. So if I take this and this, we can say that we are effectively getting a couple. So this is how I can transmit take the force of F to B with the couple or moment, which is equals to F into B. I hope this is clear to you because this will be helpful for us. If let's say we have some cross sections, uh, uh, a, is a square cross section. And, we have this is z axis and this is y axis, and we have a rectangular cross section is having dimensions like this, or a rectangular cross section like this. On this axis. This is also like axis is z, and or if I have a box section, something neglect that. Assume that this thickness is same. I have not drawn it properly, but just see that thickness of this. is same. Thickness of the box, hollow. Thickness of the walls of the box. This is 3. So, if I apply axial tensile force along x-axis, uh, which means that say this is a bar kind of thing, and this is the cross section, and you can change this cross section with various sections here. So, if I apply a axial tensile force, which of the cross sections will you choose to minimize the axial stress? So, which cross section will be suitable? Do you think that if I apply axial tensile stress, which cross section will give me efficient transfer of axial force or minimum axial tensile stress, whatever it is?
Sir, it depend upon the.
Depends on the
Audible, sir.
yeah. Tell me.
Sir, depend upon the area of cross section, sir.
Depend upon the area cross section. Okay. So you can see that I have given you the dimensions. What do you think? What are the area of the cross sections? Different cross sections. Dimensions are there. So what do you think?
All are same, sir.
All are same. So what do you think? Which will be efficient to transmit the axial tensile force or axial force?
Every beam will transmit the same axial forces. Means
Yeah. Okay. So do you think we can use anything?
yeah, for axial purpose, yes, sir.
Yeah, you are right. So because we have seen that axial force is constant across the cross section, axial stress is constant across the cross section. It doesn't vary. So regardless of whichever section you use, the axial stress which is transmitted is same. Axial stress is same on every cross section. So we don't have any uh, difficulty in choosing which section because all have the same area, so all will have the same axial stress. So it's not like one B section will have maximum axial stress or something like that. So we can choose anything. Yeah. Do you have do you feel that background noise is there?
Ah, sir, it's okay, sir.
Uh, is it very high?
No, no, sir. Okay.
Okay.
But the background image is very nice, sir.
Okay. My lot of things are there, so that's why I have to this to cover. I don't want to show my uh, clothes and also.
Sir,
Yeah,
so today your health is good?
yeah. I'm fine. Are you feeling less energy? That I am less energetic or something like that? Hello.
Not good.
Yeah. What happened?
No, sir. In the video starting time, I think I saw you that you feeling little tired, like looking like tired. So I asked.
No. I was just sleeping, so I got up and I'm taking a rest. So, yeah,
Fasting is going on Saturday.
yeah. So, uh, hi Priyanka, we were discussing this uh, problem here. So we have different cross sections, and you can see the dimensions of these cross sections also. One is a square and two rectangular cross sections, and one is a hollow cross section, and the dimensions are given. So if we apply a axial load, so which cross section will be efficient to transmit this axial tensile load? So the thing is, every cross section here, we see that uh, it has the same area. So same area, and we know that axial stresses are constant throughout the section. So the area is same, and the axial stresses are constant when we apply an axial load. So it doesn't matter whichever cross section we take, it will have the same axial stress. It doesn't affect our decision. So we can take any cross section as long as this area of this, because the area of the cross sections are same. So let's say if apply a bending moment on this, apply a bending moment, uh, which one of the cross sections will have the maximum bending stress? So if I apply a bending moment for a beam having these cross sections, so which cross section do you think will have the maximum bending moment? Which which cross section will have the maximum bending stress? Sorry.
About which axis, sir?
Yeah, this load is applied on the y-axis. Okay, so this will bend. These sections will bend about the z-axis. Let's say this is my beam, and this is my cross section, and I apply load in this. Uh, this is x, this is y, this is z direction, and this is my cross section. So obviously this will bend about the z-axis. Uh, so if I have a square cross section, it will look like this. If I have a rectangular cross section, uh, this is the this cross section. This will look like this. Load, sorry, not load here. We are just talking about bending. I'm just applying a bending something. Your bending and another cross section. The beam will look like this. This will bend about this axis. So which we know that all the cross sections have same area. So which cross section do you think will have the maximum bending stress?
Whichever has the least moment of inertia, sir.
Okay, so do you
And
which
from
one do you think will have the least moment of inertia?
from the figure, I think it is option C, sir.
Yeah. So the depth is low. Obviously, moment of inertia will be less, and moment of inertia is less, which it will lead to more bending stress. In the hollow section here, uh, it is as we have discussed in the last class, it is always favorable that the material is away from the axis. So whenever it is away from the axis, moment of inertia increases. For hollow sections, moment of inertia is high generally. So these three is using these three. What in these cross sections, this will have the maximum bending stress. Option C, because it has less moment of inertia. Okay, next let's see if I have two. I have a square cross section and a square cross section which is put like this, like a rhombus or something. Instead of placing it on it, placing on the side, it is rotated about 45 degrees and it is kept like this. Both have same sides, something, let's say A. Uh, determine the ratio of maximum moments m1 by m2. M1 is for first cross section, m2 is for the second cross section of for a beam of cross section given in these figures when they are having same bending stress. Both cross sections have the same maximum bending stress, whatever you say. What will be the area of moments? What will be the ratio of moments? Sorry. How can we proceed with this? How can we proceed with this? Do you have any idea? Like, can you suggest something from which we can go and get this ratio?
Sir, from center to the surface edge distance is vary from 1 to 2, because in 1 it is a, but in case of 2 it is root 2 by 2.
Or okay, center. Okay, a by root two. Yeah, root two by two. Yeah, that is fine. But how can we get the ratio of moments given the bending stress is same for both the sections?
Force into distance you can put, sir.
No. Yeah. So we have the see.
Flexure formula, sir.
Yeah. We have the relationship between the bending stress and the bending moment, which is given by the flexure formula. M by Iz is here. I'm just taking it as M by I is equals to F by Y. So this is the flexure formula we have, and it gives the relationship between the moment and the bending stress. So let's say for M1 this is F into I1 divided by Y1, and for M2 it is for the section 2 it is bending stress is same, so F into I2 divided by Y2. So the thing is, the axis, neutral axis is different for this. So here it is this, here the neutral axis is this. So the moment of inertia we have to calculate with respect to this axis separately. So for this it is, we know a power 4 by 12. For this also it is a power 4 by 12. So you can calculate it like you want, you can calculate it. You can take a triangle, you can take two triangles, and about this axis, uh, let's say I have breadth and B and H, something like this. About this axis, it is centroidal axis. This is BH cube by 12. bhq by 36. So we have to shift this. Uh, we have to get the moment of inertia about this axis. And similarly, there is bottom section. From here, we have to shift this. So this is you. This you can do it using the parallel axis theorem we have. Let's say I1 is equals to some Iz plus A into H square. Centroidal axis is IC plus A into H square, where H is this distance, which is generally H by 3. From base, centroid is present at a distance of uh, H by 3. So you can use this and you can get the for this section for the top and bottom, and you can sum it. You can get, you will see that this is equals to a power 4 by 12. So I'll take the ratio of m1 by m2 is equals to f is same, everything is same, so, and I'll have f is same. So I1 by 2 and I1 by y1 and I2 by y2. So I is a power 4 by 12, both are same, so I'm just taking them out. I'll get the ratio y2 by y1. So y2 means here this is the maximum bending stress we are talking about, which is present at the extreme fibers. So y2 is basic here. Y2 is uh, a by root 2. You know that uh, total rhombus, total diagonal length of a square is root 2a, and half of it is a by root 2. And we have this as a by 2. For this, it is a by 2 per square cross section. So we'll remain with 2 by root 2. Again, we'll get root 2. And this ratio of m1 by m2 is 1.414. So this is how bending stress is given. We have to get the moment. So we have to use this relation, flexure formula, which gives the relationship between bending stress and the bending moment. Okay, so we move to the next problem. We have a steel bar uh, whose dia is 200 mm. And from this we have to uh, get a rectangular cross section. So we don't want the circular, and uh, but we want to get some rectangular cross section from this. Cut out a rectangular cross section from this circular cross section, whose breadth is something b and d. So this should be cut from the circle. So cut circular cross section. So we have to determine the value of b and d such that the beam which is made from this cut out rectangular section is the strongest possible in bending. So strongest possible, or you can say strongest possible rectangular cross section should be cut from this circular cross section. So B, and for that we have to find out what is the B and what is breadth and depth we can get when we cut out from this. So self weight is neglected, yeah. Self weight neglected. So what do you think for a rectangular cross section? So if we want that it is strongest in bending, what should be maximum?
So if like sigma is like if you consider sigma is constant for a material, then it should be able to withstand maximum bending moment.
No, no, no. Sigma, the material properties doesn't come here. You have a circular cross section. Let's say you have a circular cross section beam, and from that you want to cut out a rectangular cross section here. Okay. So I want to cut out the rectangular cross section such that the load for whatever the load which I apply, the bending should be uh, should be effectively resisted, or you can say uh, maximum stress on this rectangular cross section should be less. So I can cut out different cross sections, right? Like I can cut out a cross section like this, or I can cut out a cross section like this. So if I want the bending stress to be less, not very high, if I want the bending stress to be less, then what should be maximum?
I by y, sir.
Yeah. So we know that uh, moment of inertia should be high. So what for whatever the section which we cut out, moment of inertia should be high, and then we can say that it is the strongest possible beam cut out from this circular cross section. So say Iz, let's say I will take BD cube by 12. So I have to maximize this, maximize this. But we have a constraint here. So this is basically an optimization problem. We have to find out the maximum or minimum. So optimization is basically maximum or minimum subject to some constraint. We have some constraint here. What is the constraint?
Diameter, sir. So diagonal will be equal to
Yeah,
diameter.
yeah. So let's say this is our constraint. This is the dia. So you can see that we can use the can take it as a right angle triangle, and we can see that d square is basically it should be equals to uh, d square plus d square. It is the it should be satisfied. So breadth and square of breadth and square of depth should be equal to sum of square of breadth and depth should be equal to the diameter square. This is our constraint. So now I can let's say I'll take uh, d square is equals to d square minus small capital D square minus small d square. Let's say this will be equal to root over uh, d square minus capital D square minus small d square. So now say I'll substitute this here. This d cube by 12. And now you can see that the moment of inertia is a function of d. So only d is varying. Capital D is we know that diameter of this circle is constant. So only d is varying. So I can simply differentiate it with respect to uh, small d. Okay, I'll just small d. So if you differentiate it, you can see that 3d square. First, UV rule I can use differentiation. Right, 1 plus 1 by 2 d square minus d square and minus 2d into d cubed. So this should be equal to 0. So for maximum or minimum, uh, we take this differentiation should be equal to 0, and we can get like this force, and this is d power 4 by this power this. So if I take this side, okay, d square 4d square, and this is d square minus d square. So I'll get yeah, have this 12. Twelve, 12, 12. So this is 4 threes. This is 3. D square minus 3d square. 4d square is equals to 3d square. So we'll get d square is equals to 3 by 4 d square, and eventually you'll get root 3 by 2 d. So this is d, and we want b also, which is d square is equals to d square minus 1 d square. D square minus 3 by 4. So we'll get d square by 4 d by 2. So this is these are the dimensions of B and D, which can be cut out from the circular section, such that the uh, it is the strongest possible section cut out for bending. So this is the uh, and you can see that taking the constraint should be satisfied. D square plus d square should be equal to the diameter square. These are the dimensions for it. So D is uh, so we know D, capital D. So from that we can find out the small d in mm. We can get I think So 3 by 2 to 200, 173, 173.205 something mm is the we cannot properly uh, cut equal to some 0.25 something like that. So we can nearly say 173 or 175. And B is equal to 100 mm. So this is how we cut the section from this circular cross section such that the bending stress is minimum, or the section is the strongest for the bending moment which is applied. Okay. I hope it is fine. If you have any doubts, you can ask.
Clear, sir.
Okay, chalo. Okay, so next we'll take this question. So we have a design problem with simple homogeneous beam subjected to some live load WLF, live load which is say WLL, small WLL, kilonewton per meter, something like this. And it has a box cross section. The cross section looks like this. This has a width 140 and these are the axis directions, x and y coordinates, and this thickness is 15 mm, and this is also 15. Overall, the wall thickness is 15 mm, and this is 200 mm. Depth is 200 mm. So whatever I have drawn is not to scale, so don't take it. It looks like a square, but it is a rectangular section. And the beam, let's say this is a simply supported beam. So this is the beam, and for which the cross section is given. It's simply supported beam. We have some uniform distributor. Live load. This is the live load. This has a length of 2.5 meters. So the material has a permissible stress is sigma p, let's say, which is 150 megapascal. So the maximum bending stress should not exceed this. If it exceeds this, the material will fail. So we don't want that to happen. So we have to keep this in check. And the unit weight of this beam material is 78.5 kilonewton per meter cube. Okay. So, what will be the maximum live load that can be applied on the beam? First question is this. Maximum live load WLL in kilonewton per meter such that beam is safe for this cross section. This is the first question. So, how are we going to solve this? What should we do? How should we proceed?
So, so,
Yeah.
so first, we can find moment using the flexure formula, the maximum moment it can withstand.
Hmm. Okay.
Then, uh, then if we draw the bending moment diagram and find the maximum moment, and if we equate it.
Yeah. Absolutely. It's correct. So we know that flexure from the flexure formula. So bending moment and bending stress is can be related like this. M by I say Z M by Z should be equal to uh, here the permissible stress F by Y. Okay. Generally, I'll write uh, Y. For this cross section, so permissible stress is given, and Y is I know the extreme length, which is Y is general. Here it is 200 by 2, which is 100, and sigma P is also can say given 150 megapascal, so Newton per mm square, and M by Iz equals to 1.5. So what is Iz here? Iz. Iz we have to calculate for this box section. So dimensions are given. So I'll take the moment of inertia of the uh, rectangle for the outer dimensions, and the moment of inertia for the rectangle with inner dimensions, inner rectangle, and I'll subtract it from the outer rectangle. Then I can get the moment of inertia. So 140 into, so basically 140 into 200 cube by 12, and the inner dimensions are yeah 110 into 170 cube by 12. So whatever you are getting it, you just cross it. Yeah, this is 4829750 mm44. This is the, and m should be equal to 1.5 into this 4829750. Okay, here this moment should be equal to the bending moment of the beam. So maximum bending moment of the beam. So for a simply supported beam, where will the maximum bending moment occur? For a simply supported beam, for which the load is a uniform load applied like this. where will the maximum bending moment occur? It will occur at the center. We know it, middle of the beam. Okay, and the bending moment diagram will look like this. It's a parabolic. The bending moment diagram is parabolic, and this is the maximum bending moment at the center, and which is equal to WL square by 8. So the L is length of the beam, W is the load. Okay, we know this, so I don't think we need to discuss this. So we have to remember this. So all the formula with respect to the simply supported beam, cantilever beam, maximum and maximum bending moment. So here W L square by 8 should be equal to this, whatever we get. But here they have given the self weight of the beam too. So we have to include it, self weight as well as the live load. So self weight also is kind of uniformly distributed load. So that's why they have given. So W should be equal to WLL by W self weight, okay, into L square by 8. We have to make sure that self weight is also included here because it is explicitly mentioned. So gamma is given in 78.5 something kilonewton per meter cube, right? Okay. And from this, I want to calculate the self weight WS should be given, it can be given by uh, weight per unit volume into the area of cross section, right? So area of cross section of this beam into the area of cross section. So area of cross section of this beam, again you can find out by subtracting the inner rectangle from the outer rectangle. 140 into 200 minus 170 into 110. You will get 9300, 78.5 into 9300 is in mm square. So square, I want this in meter square. So I have to multiply it with 10 to the power of minus 6. So ultimately I'll get the self weight as 78.5 into 9300 into 10 to the power of minus 6, which is equal to 0.3005 kilonewton per meter. Also, you can say that you can say this is also in Newton per mm. So whatever. So or Newton per mm also we can say this. So WLL plus 0.73005 into 2.5 2.5, right? So 2.5, if I take this in mm, uh, 2 point length of the beam is in meters, so I'll take this in mm. So 2500 square by 8 should be equal to 1.5 into 48297,500. So let's see what WLL plus 0.73005. So if I do this calculation, everything, get 48297 about 0. Yeah, 28 2500 square. Get this 97.7312, and the live load is equal to live load which we should get. So the maximum live load which we can apply is 92.00155. So is in kilonewton per meter. So this is the maximum live load which can be applied on this field given the maximum stress, permissible stress is 150 megapascals. If we go beyond this, uh, the section will fail, eventually leading to the failure of the wheel. Okay, this is fine. I hope. If you have any doubts, you can ask.
No, sir.
Okay. Let's say if I replace this box section uh, with the square cross section. Replace the box cross section with the square cross section. What obviously having same area of same area. What should be what will be the maximum live load which can be applied? So we know that given that the cross section is square and the area of cross section is same as the previous one, so I have to find out the dimensions of this square. So a square is equal to this 93.9300 and this is the area of cross section of this box section. So I'm equating it to the area of cross section of square. So I'll get the dimension of square as 96.436. So so this is this a 96.436 5 something. So now I need to calculate what is the moment of inertia for this a power 4 by 12 96.436 5. Like we'll get 720747497 7207497 0.725 mm power 4. This is our moment of inertia. And we know that again we use the flexure formula. Permissible stress is same for the material, right? So here y is basically from extreme fiber, which is equal to a by 2. So m is equals to 150 into a by 2. A by 2 is 96.4365 by 2. into 7207 over 9, 0.72. So if you do this, get something m is equals to 22421482.8. And again, so we know self weight plus live load into L square by 8 to this. So self weight is same 0.7 3005, and this is 2500 square. So again, if I do this, I'll get WLL this will give me 28.69949 something. So live load is maximum live load that can be applied on this cross section, square cross section beam is this kilonewton per meter. So you can see that for same area of cross section, box section uh, has greater moment of inertia. That's why it will take more load compared to a square cross section. So permissible live load for a box section is 92 point something kilonewton per meter. Here it is only 27.969. So we can see the effect of moment of inertia for different sections. Okay. Next, if I have a rectangular cross section, not a square but a rectangular cross section, whose aspect ratio in the sense depth by breadth of this rectangle is 2 by 2.0. So depth is twice the breadth. So this is the rectangle. Okay. So for this, what will be the maximum live load? Again, area of cross section of this is area of cross section of this rectangle should be equal to uh, the same area of cross section of the box section which was given 9300 mm square. So D as we know is given 2D 9300, and you know 9300 by 2. So B will be 68.1909 m, and D will be twice of this 136818. So this is these are the dimensions of the dimensions of the cross section. So again, we have to calculate the moment of inertia. I think BD cube by 12 for a rectangular cross section. you will get 68.190, 136.38, 187. Sorry. Get this moment of area of cross section, moment of area, sorry, area of moment of inertia, and power 4. So again the flexure formula m by I is sigma by, here it is d by 2. Okay. So sigma is 150, so d is 136.38187 by 2, and into this uh, 988.7, okay, into you get 317.08735.27, and again we know 2500 square by 8 equal to something. We'll get this plus this equal to 40.587 So removing the self weight, I'll get the maximum live load which can be applied on this rectangular cross section beam is this. Okay, kilonewton per meter. So you can see that for the earlier square cross section, uh, depth was 96, but for this rectangular cross section the depth is 136.387. So depth increases obviously will give me more moment of inertia, and more moment of inertia means more load it can take. So that's why we can see that the permissible load is increased compared to the square cross section for the rectangular cross section. See is the okay. This is for a rectangular cross section. Suppose if I have uh, circular cross section with the same area, circular cross section with same area as the box, what will be the maximum live load which can be applied? So we know that 5d square by 4 should be equal to 3000, 9300, and from that we can get the dia of this equal to 9300 4 5 square root of this. We will get diameter of this cross section for this area is this something. Yeah, this is the diagram. Just doing it so that we can appreciate how the cross sections affect whatever maximum bending stress or the load carrying capacity of the. So for circular cross section, moment of inertia about this axis ZZ is let's say this is the axis Z pi d power 4 by 64. So this is about this axis. Okay. Last in torsion we have seen that we take the polar moment of inertia, which is the axis which goes into the plane of this paper. So uh, that is pi d power 4 by 32. This is pi d power 4 by 64. So basically you can use the perpendicular axis theorem. So about this, and you can get the polar moment of inertia. I think you know that. So for this, if I calculate 108.86 something moment of inertia, get hope you're doing it and getting the same answers which I'm getting. If you are getting something wrong, you can tell me. Okay. If I'm getting something wrong, and if you feel that something is wrong, you can tell me. So this is the moment of inertia for this circular cross section. Again, we go to the Flexner formula. Permissible stress. Here, this is diameter by 2. The distance of the top fiber from the neutral axis is delta by 2. So can take, I think, should have taken capital B, but it's fine. Into IZ. So I'll get 150 by 2, 150 2108 816 by 2 into in power 4. I think 1897.4930.8. Again, bending moment for a simply supported beam subjected to uniform load is maximum at the center, middle of the beam. L square again 2500, length is same. Okay. So you can get W S plus WL equal to 24.287, and live load can be calculated by subtracting the self weight, and it is equal to 23.786 kilonewton. So this is the live load, maximum live load, which can be applied for this circular cross section. Did you get the same answer for it?
Yes, sir.
Digit, after decimal, I take 2 digits, so little variation is there, but nearly the 24, 23 up to.
Okay, okay, it's fine, it's fine. Yeah, you will get a range, so you can answer it appropriately. So we can see that how the maximum uh, live load which can be applied uh, varies cross section to cross section uh, because the moment of inertia of a box section is very high. It can take maximum live load which can be applied. You can see that in a box section, uh, basically the material is away from the axis of neutral axis, or the axis from which we are calculating the moment of inertia, or the moment, or the axis about which the bending is happening. So that's why, as long as the material is away, it will give me maximum. It will give me the maximum moment of inertia, and maximum moment of inertia is more resistance. More resistance means it can take more load. So that's why 90 to something which you get. Okay, and we have also seen how depth can give me effects compared to this, and these, so maximum moment of inertia will lead to low bending stress. Low bending stress means it can be less lesser than the permissible stress, and low bending stress, and it can more live load can be applied. So subject to everything is same, subject to length is same, area of cross section is same, but moment of inertia is vary. So that's how we can see various effects. So from this, we have seen that the most efficient cross sections, the most efficient cross section in terms of bending based on solving the above problem, like for different cross sections, we can say that box section resists bending with very high efficiency, and it is stronger compared to the other cross sections. So compared to the solid square, solid rectangular, and solid circular box section, uh, all obviously assuming that area of cross section of all these sections is same. So if a material is given, uh, the flexural rigidity given a material, the flexural rigidity in beam analysis increases when the material is placed farther away from the centroid of the cross section. So we have seen this. Farther the material is away from the centroid of the cross section, we can see that in the box section, centroid is present, but the material is far away from the centroid of it. So that will lead to a more uh, moment of inertia, and more moment of inertia is obviously will lead me to higher flexural rigidity. Flexural rigidity is E into I. So if the material is same and moment of inertia is maximum. So E into I will be maximum, and that's how it can affect. And okay. So whatever we have learned in this week is only applicable for beams having cross section with a vertical plane of symmetry. So we are not discussing here cross sections which don't have a vertical axis of symmetry, or let's say like this or something. So there is no vertical axis of symmetry, or the loading axis is not dividing the cross section into symmetric parts. So if this kind of sections are coming, so whatever we have discussed is not applicable, because in addition to the bending there is also twisting which occurs. So that we will see in the uh, next coming, I think in coming weeks there is some section on unsymmetrical bending. So unsymmetrical bending, and also Euler-Bernoulli beam theory, whatever which we have discussed, is only applicable when the depth is less. Okay, so if the depth is very high and it is generally we take the length by depth ratio. So if this depth increases, this ratio will get decreased. So if depth increases, what happens is that the section is not perpendicular to this, because shear also comes into action. So this is limited to the understanding which we have got is limited to that depth is small. If the depth increases, we have to go for other beam theory, which is Timoshenko beam theory. There we'll take the shear effect also. So in this week, whatever we have discussed is simply pure bending. So pure bending is we are assuming that there is only uh, bending moment acting, and for that we are uh, taking for that we have discussed various things, and we can also see there is also effect of shear. So effect of shear can be neglected for thin beams, which for which the depth is less. But uh, this is for engineering analysis. Engineering analysis is we may whatever the maximum load that can be applied, we make sure that it is very less compared to the permissible load. Then we can neglect certain things. Okay, so that's how we take a factor of safety and design various things and all. So shear force also is there in beams. Shear force also comes into picture. That we will see in the next week, coming week, where we see that shear force is maximum at center, and at the free ends, free surfaces, shear force is zero. Like we have, I think it was discussed. Like it has a parabolic variation basically. So effects of this we will study in this next week, coming week, shear uh, and different things related to that. The thing is, whatever we are doing, we basically took axial stresses, we took torsional stresses, and then we came to bending stresses, and then we will see shear. Because we are taking the because we are operating in the linear zone. So linear zone means uh, principle of superposition is valid here. So principle of superposition is valid. So if I have different things acting simultaneously, like bending, shear, and torsion, uh, everything is acting axial force. axial stresses, different things are acting. If if I am in the linear zone means obviously the deformations are very small. Uh, if I am in that zone, I can sum all the effects and get the net effect of that. So that's the advantages of that is the advantage of being in the linear zone. We can sum the various effects. We can calculate the uh, uh, single effect separately due to bending, due to axial force, due to torsion, whatever, like everything is calculated separately and you can sum it up accordingly and that to give the net effect. So this is only applicable for the linear analysis. Okay, when we go to non-linear, that is like things become more complicated and we cannot do the simple superposition. So superposition is valid only in linear zones. So non-linearity is like another. Uh, you can say you can do this if you go to masters. You can learn about non-linearity. Very complicated thing. We have material non-linearity, geometric non-linearity, different things. So, I think I will stop here. If you have any doubts, questions, you can ask me. I will try to answer.
Sir,
Yeah.
uh, this is up to sir. This is clear. Sir, what should be the L by D ratio? So on that case, we consider it is a we go for the Bernoulli's this equation. Otherwise, we move for the another equation. So what is the
Okay. Okay. Uh, Forgot actually. I'll just see. Divided ratio for so it is given that length to depth thickness, length to depth of uh, beam should be 20 and above. So if it is 20 and above, then you can take the Euler-Bernoulli beam theory. If if it goes below this, then you cannot use the Euler-Bernoulli. This is just kind of notional, like somebody has taken it. So basically, we are neglecting the transverse shear effects. If it is greater than this, you can take Euler-Bernoulli. Less than this, we have to go for Timoshenko. So Timoshenko is obviously won't study in this course. Advanced concept. Yeah.
clear, sir?
Okay. Any other thing?
Sir,
Yeah.
like I have a doubt, not regarding the subject, sir.
Okay. You can
Uh,
answer.
like regarding like post graduation, sir.
Okay.
Uh, like uh, if we are pursuing like MTech degree, then does it mean that we should continue with PhD or we can opt for a job? Like how is it?
No. You can do whatever you want. You can go for a job. You can do PhD. Uh, it's not like you have to do PhD. PhD is an option. You can go for jobs also. There are many jobs you can opt for. Like industry also has different roles for postgraduate students, graduate students.
Okay, okay, sir. I like like after taking this course, like I have developed interest in like specializing in designs.
Okay,
So
design. Hmm.
like design subjects. So, like if that is the case, like which is the best like way to do it? So like
Okay. So I'll tell you. You are from mechanical engineering domain.
yes, sir. Yes, sir.
Okay. So in mechanical engineering, I think machine design is uh, a specialization in MTech, I guess. Machine design, thermal, and manufacturing. These three, and also different other things are. But if you are interested in design, you can opt in MTech for machine design. So MTech in machine design, especially if you want to go for design. So if there are also other like thermal manufacturing, those things are different, and also you can go for interdisciplinary things also. Like I think you can go in aerospace. Aerospace also you can go. Aerospace structures, MTech specialization is there. You can go for that also because you are from mechanical. You can opt for that too. And if our department and also professors department is applied mechanics. So here we have computational engineering. Some MTech specialization is computational engineering. So it is not related to design, but you can uh, do different how you can learn related to aspects related to solids, fluids, and something related to design. So one one area can be that. So I think these three options you can explore for MTech if you want to do MTech. From let's say from if you want to do from IIT, yeah, these MTech options are there. And the other thing is if you are interested more towards research, you can opt for MS also. MS is a program which is like a mini PhD. Okay, in MS, basically it is of 2.5 to 3 years. So the focus will be more on research. You'll go deep in one particular aspect. You take a problem and you go deep into that, and you do some research. MTech is like a comprehensive thing. Like MTech you have to take more courses. I think some 6 to 12 courses you have to take. In MS, I think 5 to 6 courses are enough. Obviously, you can if you want to do more, you can do. Uh, and also that the thing is, MS people have more uh, strength in that area. MTech people usually dabble in different because you take courses are very high. Courses are very high. The research part comes only, I think, in the last semester. You don't do that much research. Like it is a part of your grading, but it is not a, hard and fast thing. In MTech, there are some credits for project work, but in MS, the research work is the most important thing. So MS, if you are more inclined towards research and you want to do, you know the area which in which you want to do research, then you can opt for MS also. That is an option.
Okay, so like in MS, like like if we are particular about that subject, then MS is a better option. Like,
Yeah. Uh, the thing is, uh, you think that you want to do something, uh, and that you are interested in something, but when you go and explore different things, you develop interest in other things also. Like initially, you want to do in machine design sometime, like let's say you uh, you study some other subject and you get interest in that, you can um, develop in that also. Sometimes, if you are very clear, you can go for MS. That also depends on MS. Whenever you take, it depends on the faculty. So faculty, uh, you will be assigned to a faculty like you are assigned to a faculty in PhD. You have a guide, so he will. Uh, you have to discuss the topic with him or her, and according to his area of specialization, you will work. So you should be prepared. Like you should be prepared like MS for MS. If you want to go, you give you. If you want to take an admission, you will have an interview. I think mostly interview. Written test is like some IITs take it. Not necessarily every IIT will take, but interview it will be there, and the emphasis will be more on the interview. Gate score is, I think, there will be a minimum criteria for the grade score, but interview is the main thing. So, and you should be prepared like you should look at the faculties profiles, different faculties, and in which areas they are working, what are their research interest, and you should uh, after joining. You should meet them and discuss with them that you want to do this, you want to explore in this topic. And if you have any problem, you can directly say, like a research problem, you can directly discuss with them. Or if they have something which aligns with your research interest, they will give you something. So that that thing happens. Yeah. So obviously you can do, you can get a job also after MS also. So MS also, um, it's not like you have to do PhD after MS. You can get a job after MS also. In fact, sometimes it becomes more helpful because you are more, uh, if you have taken some industry related problem and if you have gone deeper into it, um, you have more chances of getting a job compared to an MTech candidate because you will have more experience working on the problem.
Okay, sir. Thank you, sir. Thank you very much, sir.
Yeah. Yeah. You are you in second year or third year?
No, sir. I have graduated, sir. Right?
Oh, you have graduated. Okay. Okay. Oh, you are preparing for something?
Uh, Actually, planning to prepare for grades, sir.
Okay, okay, okay. Then you have you can explore because you have time, so you can see different things. And okay, if there are any other doubts, you can ask me. Otherwise, we can close it for today.
Sir,
Devashish, I can't hear you. Uh, your voice is not audible, Devashish.
now I'm audible.
Yeah, yeah, yeah.
Sir, in IIT Madras for MTech, what is gate score required, sir?
I don't know. I think maybe some 600, uh, depending upon the category. I think open category it is about um 700, above 700, 650, above, I think, maybe. Yeah. It depends. Like in last few years, it has dropped, I think, because people don't want to do MTech, so they want to go for jobs. So IT was booming, so people wanted to go. So lesser people are preparing for GATE, and also engineering services posts have dropped, so people are not. Railways was not offering it, so people have dropped preparing for it, and they are going for IT, and all. So it has GATE score has reduced. That is the thing. So I think 650 above should be fine. I don't know. You can
Am I
check in
audible,
the
sir?
website. Yeah, yeah.
Sir, could you suggest me which IIT is very good for the research in the renewable energy sources or renewable energy? About this topic, the research they made good, or
See,
IIT Madras?
yeah, I'll tell you what the thing is. See, there are two things, okay? One is the institute and one is the guide. So, uh, if you get a good institute and